Welcome everybody to the Griffith Observatory. You guys are looking at one of our most popular exhibits because it's right at the entrance. This is called the Foucault Pendulum. So when you look down here you see numbers, and so a lot of people first guess that this is actually a clock, but it doesn't tell time at all. Instead, this pendulum is here to prove something that we kind of take for granted, something we learn in school when we're really young, and that's that the Earth is constantly spinning around. So right now you're spinning at about 850 miles an hour. But if someone came up to you and said, prove it, it'd be really hard. And that's because you can't feel it and you can't really see it. Well, this pendulum is one of the only ways that we actually can prove the Earth is spinning. And it works in a pretty simple way. You just pull the pendulum back and you let it go. Once you do that, it's going to start swinging back and forth. But the pendulum will always swing in a straight line. It can't change direction all by itself. That means that the pendulum can't move this way, but it also can't move that way around the circle. It can only swing straight. Well, then the next question is, why do those pegs fall over? Because you'd think if the pendulum just swung back and forth in a straight line, then the pegs would just kind of sit there and they would never fall. But one peg does fall about every 6 minutes, and the reason for that is that underneath the pendulum, the entire Earth is actually spinning counterclockwise like that. So the idea is that we take those pegs, we lower them down and set them at the bottom of the pendulum pin. Then all we have to do is wait. And what will happen is the Earth will spin counterclockwise like this, and it'll actually move the pegs slowly with it around the circle until one by one, the pegs just happen to cross the path of the pendulum, which is swinging back and forth in a straight line. So that's how this pendulum actually proves the Earth is spinning. The easiest way to kind of visualize it is to imagine this metal ring and all of us actually going around the pendulum like that. That's what we're actually doing. And in fact, in about 42 hours, you go once all the way around the pendulum one time. That's why we have 42 different sections, and that's what those numbers are for. Like I said earlier, you spin at about 850 miles an hour. That's the speed that we're spinning right now. That speed actually changes at different places on the Earth. So if you want to spin faster than that, all you actually have to do is walk that way. And when you walk that way, you're walking south. And when you walk south, you're walking to a place on the Earth where the Earth is actually thicker around, thicker in circumference. By the time you get to the equator, the Earth is about 25,000 miles around. And what that means is that every single day in 24 hours, you're actually traveling 25,000 miles. Traveling 25,000 miles in 24 hours works out mathematically to be about 1,000 miles an hour, a little bit over. So that means you're actually traveling at about 1,000 miles an hour at the equator. The opposite of that, of course, is at the North and the South Pole, where what you're doing is you're just standing in one spot and you're spinning. So you can imagine that's the North Pole. In 24 hours, you spin around one time, but you didn't actually go anywhere. You traveled 0 miles. That means, since you traveled 0 miles in 24 hours, you actually spun around at 0 miles an hour. So at the North and South Pole, you spin at 0 miles an hour. At the equator, you spin at about 1,050. Here in LA, you spin at about 850. Does anyone have any questions? Yes?
How do those pegs get back up?
We have a big, long stick, and we just pick it up and move it over. Pretty simple. We'll do that in about 10 minutes. It takes about 6 minutes for each of those pegs to fall. Toward the end of the platform, it actually takes a little bit longer. Pegs get further away from each other, kind of.
How can you spin when you're going 0 miles an hour?
You can spin around. You're just spinning at 0 miles an hour because you're not actually going anywhere. So when you're spinning, we're talking about, when we talk about miles per hour, we're talking about how many miles, you can think about it exactly how it is, how many miles you're traveling in every hour. So if you imagine yourself at the North Pole, you're standing right here. And in 24 hours, here's what you do. You stand in one spot and you spin all the way around. You didn't go anywhere. You moved 0 miles. Even though you were spinning, so this is just a spin, it's not actually traveling anywhere.
The distance is 0.
The distance is 0. You actually move 0 miles. It doesn't matter how long it took you to do it, it's still going to be traveling at 0 miles an hour. Because you went 0 miles. Once you get off the North Pole, you start making very small circles around the North Pole. The way you can really think about it is that at the North Pole, all you're doing is twisting or spinning around. and at the equator, all you're doing is moving. So basically, you can either be twisting or you can be moving. And what you do is, as you go from the North Pole to the equator, you turn your twisting into traveling or into moving. The more you get off the North Pole, the more you turn that twisting into moving. So you can imagine it's like a scale. You get somewhere in the middle by the time you're around 45 degrees. Anyone have any questions?
The pendulum was.
So at noon today, the pendulum was in line with that arrow you see at the bottom. This pendulum takes 42 hours to look like it goes once all the way around the circle. That doesn't divide into 24 hours, which is the amount of hours in a day. So what we do is every day at noon, we reset that arrow in the middle and line it up with the pendulum again. So at noon today, someone lined up that arrow with the direction the pendulum was swinging, like right like that, let's say. Then over the course of the next 6.5 hours, slowly the Earth turned like that, and it moved the arrow so that now it's facing this direction. That's all that happened. We don't reset that arrow, so that shows you just how much the Earth has appeared, or how much the pendulum has appeared to move, how much we've actually spun underneath it.
So from the pendulum is going not at zero, but it's going like a little bit to the in between the 0 and the 1 section.
So as we wait here, the pendulum will just slowly look like it's moving like this. So it just has to do, that's where it happens to be right now. If you were to wait about a half an hour, it would be right in the middle of the 1. So it'd be swinging between the 1 and the 22 over there. And so what will happen is over the course of the next 42 hours, the pendulum will look like it does this. Hit every single number, go all the way around, and in 42 hours it'll be swinging exactly in the same direction. So the actual numbers that it's swinging between are totally meaningless. It doesn't really matter. They don't tell the time. They don't really tell us anything about the time of day or anything like that. They're only there to keep track of how long it takes for us to go once all the way around the pendulum.
So the only thing that's moving is that?
It's us. Yeah, it's us.
Moving, that's not.
Exactly. So if you were to look down from outer space, what you would see is that the pendulum would always be swinging back and forth in the exact same straight line, just swinging, 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 that's it. You can twist the pendulum all you want. I could twist the string if I wanted to. It's still swinging in a straight line. I could actually hold this. I can walk around it. It'll still swing in the exact same straight line no matter what I do.
So you're saying the whole everything, this is
Yeah. So the easiest way to think about it is just think of yourself in front of that number. I'm in front of the number 13, right? So what will happen is if we waited 1 hour, I would still be sitting right in front of this number 13. You would be right in front of the number 17. But what actually would have happened is this whole metal ring would have moved like that. So now this 13 would actually be where the 12 is in space, right? So this whole thing would move. We don't feel it. And then the pendulum, because of that, would look like it moved that much this way because we actually moved in that other direction, right? So if you were over there by the 23, let's say, you would be standing right there. In 1 hour, that whole ring would have moved. This whole thing would move to where that 22 is. So you'd be pretty much lined up with the pendulum. From where we're standing, it was like that. So as long as you're only spinning the pendulum, that doesn't actually change the direction it swings. So you can have the building spinning all you want, that doesn't change the direction the pendulum swings. Okay?
but we see that.
Exactly. So we see it swinging back and forth, and for us it looks like it's moving like that. No problem. Any other questions? I encourage you to take a look at our white light image of the sun straight down that hallway. That is a live image of the sun. That will not be up very much longer as the sun will set before too long. Right down the hallway, that bright